Great. Okay, so today I'll sort of remind you about scanning and talk about two different models of the scanning map. Yeah, and talk about sort of scanning in the limit theorem. So talk about scanning for configuration spaces. I owe you a slightly more rigorous definition of the degree of a section. And then we'll define relative configuration spaces. We'll construct the scanning map in two different ways. I think we'll construct the scanning map, then we'll talk about relative configurations, then we'll talk about another model of the scanning map, and then we'll talk about homotopy colimits. Okay, so remember T with a dot over at M so this is the fiberwise one-point compactification of the tangent bundle. And it's a bundle, and the fibers are n-spheres, assuming M is an n-manifold. And the fiber over M is naturally just the one-point compactification of the tangent bundle of M. So, Tm, M, this is the tangent space at the point M. This is isomorphic to Rn. And then when you one-point compactify it, it becomes isomorphic to Sn. And, maybe a productive way of thinking about it is that sections of the tangent bundle are vector fields on your manifold, and sections of the one-point compactification of the tangent bundle are vector fields that are allowed to be infinity in some places. And here we're, just adding one point at infinity, as opposed to, you could add like an Sn minus 1 at infinity or something like that. Okay, and the so we'll let M be the interior of a manifold with boundary M bar, within the boundary is delta M, and we'll define the space of sections relative to the boundary to be the space of sections of this this bundle. So these are, you should think of these sections as possibly infinite vector fields, and then we require that the sections take value infinity on the boundary. And and so with the subscript k here is going to mean the subspace of degree k sections. And last time we defined the degree of a section as the signed intersection number of the section with a zero section. So if you go back, so a section is this vector field that's possibly that sometimes is infinity, and what you do is you count how many times the vector field is zero, and that's the degree. But you need to sort of count this correctly. Yeah, and I'll give you sort of a rigorous and homotopy theoretic way of how to count zeros of this section correctly. Okay, and so there's the theorem due to Dussel-McDuff and Graham-Siegel says if you have a connected manifold, then there's a scanning map that takes the configuration space of k points in M to the space of degree k sections with this boundary condition infinity. And this map is an isomorphism in homology in a range increasing with a number of points. So, you have this, so I guess it says as the points tend to infinity, homologically you can think of this configuration space as being the same thing as the space of possibly infinite vector fields of degree k. And this map is going to be it's called a scanning map, so it's going to be one of those you move your disk around your manifold and you record what you see maps. And I'll define that more later. Yeah. So any questions on the statement of this theorem? I'll construct the map rigorously, and I'll give an alternate description of degree soon.
The geometric intuition behind this map is again the same thing, right? As the other things that we have called scanning maps. Just like think of locally and move around point by
Yeah,
point.
yeah, yeah. So what you're, yeah, I mean, I'm going to define it, but basically, you're going to like zoom in and record what you see. So basically, what we need is a way of taking like something in conf k and like a point m, and we need to like, or maybe I should say, given m, what we need is we need a map from conf k to uh, to the tangent fiber. And what you do is, you just like look at your point m, look at a small disk, and then you make the disk small enough so you see at most 1 point or 0 points. And if you see 1 point, well, that's a point in a disk. If you see 0 points, that's like the point at infinity. And you identify a disk with Rn. Yeah, so that.
Oh, okay. So then if you just see 1 point, then you know that you have to send, so the map has to send to this TM at this point M, because it's
Yeah,
the
so
only
what you
point.
do is you say, maybe you think of this point as like a vector going to that point. And then if you see 0 points, then like the vector is infinite length. This, I'll give like a slightly slower and more rigorous construction, but this is sort of the idea. And here you have to identify the disk with Rn. You pick a disk around the manifold. That's this. The 1 point compactification of the disk is the same thing as the 1 point compactification of the tangent space, or you could pick a homeomorphism between them. And then if you see 1 point in your small disk, you draw an arrow. If you see no points, it's an arrow. It's the point at infinity. And you just pick your disk small enough so you don't see 2 points. Is going to be what this map is. Yeah, and like a few weeks ago, I gave a description involving like you think of these as charged particles, but we're not going to be thinking about it that way today. Okay, any other questions? Okay, yeah, but I owe you a better definition of degree. So we'll talk a little bit about the cup product. So the cup product for any space gives you a map from the ith cohomology tensor, the jth cohomology, to the I plus jth cohomology. But if your space happens to be a compact orientable manifold, then the cohomology, of dimension n is isomorphic to the homology. So you get a map on homology called the intersection product. I'm not sure what the name is. I think like this is actually notation for cap product, but I don't know. It seemed like a good name. Yeah. So what I'm going to do is I'm going to tell you like if you're how to think about this map on homology geometrically. And that will tell you sort of, well, hopefully maybe even give you intuition for the cup product. I won't tell you what this map does on all homology classes. I mean, the definition is just it's Poincare dual to the cup product. This group's isomorphic to that group. This group's isomorphic to that group. This group is isomorphic to that group. So we get a map like this. But I'll tell you, if your homology comes from a submanifold, what happens? So yeah, so let's say we have this manifold M, and we have M1 and M2, and we have Fi from Mi into M are embeddings. So if you want, you can just think of M1 and M2 as being being submanifolds, or you can think of them as being abstract manifolds with a choice of embedding. Yeah, I guess I should say, let's say everything's compact. And so we're going to let n be the intersection of the images. Maybe I'll just draw a picture first. So so what this theorem says is that the fundamental class of n, which we can view, saying the fundamental class of n, which we can view in, this is going to live in the cohomology of M. It's saying that, it's saying, I guess, two things. One, generically, this intersection is a manifold. Generically, it's a manifold of dimension. I think, did I flip this? This number is, no, this is correct. Yeah, so generically, this is a manifold of dimension I plus j minus n. You should think, so it gives you a homology class. The fundamental class of n is can be viewed as a homology class in M of dimension I plus j minus n. And it's saying that is the fundamental class of M1 intersection product fundamental class of M2. So this Poincare dual to the cup product, its interpretation geometrically is just, if your homology classes come from manifolds, you just intersect them. Maybe I'll draw a terrible picture, so it's like we have, the purple is M, we have, let's say M1 in gray. Oops, I don't know why the picture disappeared. Sorry, let me redraw this picture. Okay. We have M. In green, we have M1, which is this loop. It goes around the back too. And then we have M2 in red. And then, the intersection point, which I can't draw, is N. Yeah, so what I'm saying is you can think of, if your homology class, the fundamental class of M1 and the fundamental class of M2 give you homology classes in H1 of M, and N gives you a homology class in H0 of N, and it's saying that the homology class associated to N is just this intersection product of the homology class of M1 and M2. And they need to intersect, what's called transversely if you've taken differential topology, which is some generic intersection property. Any questions? Okay. So yeah, so this is what the this Poincare dual to the cup product does. Okay, so the old definition of orientation was, you can think of it as it's the number of points in the section applied to the manifold, and then intersect the zero section. So we have T and dot, and we have the manifold, and then we have our section, sigma, and we're counting how many times sigma is 0, which is the same thing as saying we're going to count how many times the image of sigma intersects the image of sigma 0. Okay. And so the new definition is that the degree of sigma, what are we going to do? You're going to apply sigma and sigma 0 star, so this means map on homology, to the fundamental class of M. So they're both maps from M into the this fiber-wise compactification of the tangent bundle. And so, these, fundamental class of an element in top homology, this gives us two elements in Hn, Tm. Tm dot is going to be a manifold of dimension 2n. So what we can do is we can take the intersection product here, and so this is going to live. This 0 here, 0 is n plus n minus 2n. So the dimension of the domain of sigma plus the dimension of the domain of sigma 0 minus the ambient dimension, so that gives you 0. So this intersection product, gives us a class in H0, and if the manifold is connected, then the one-point compactification tangent bundle is connected, so this is just Z. So we just define the degree of sigma to be this homology class, which is naturally identified with Z, so you can view this as an integer. And then in the case that sigma and sigma 0 intersect generically, you can use sort of the geometric description of the intersection product. But this, by definition, this product is this is a completely rigorous thing, because this, if you believe cup product exists and you believe in Poincare duality, then this definition makes sense. I've not claimed that I've proven the new definition and the old definition agree, but hopefully the new definition is rigorous. At least, if you view intersection product as just Poincare dual to the cup product. Okay, any questions on either what is the new definition or why heuristically it agrees with the vague old definition? Okay. Yeah, so this is this is how you define degree of a section. Oh yeah, so maybe just state this. So if tangent bundle is trivial and M is compact, then these space of sections becomes just a mapping space, because the bundle is trivial, so it maps into Sn. And if the manifold's compact, well, then this condition about the value on the boundary is, so if M has no boundary, then this condition is vacuous. So the section space is just the space of maps. And the proposition says that the degree of a section here is just the induced map. View your section as just a map to the sphere. Well, look at the induced map on nth homology groups. That's going to be multiplication by the degree. So yeah, so in particular, if M is this, okay. Oh yeah, any questions? So yeah, this is just saying degree is slightly more concrete when the tangent bundle happens to be trivial. Okay, so yeah, so when we constructed the scanning map for 3 abelian groups, we talked about how to build this disk bundle. So we pick a Riemannian metric on the manifold. So that means you pick an inner product on each tangent space, and then we're going to let disk M be the subspace of the tangent bundle of vectors of length less than or equal to 1, and the sphere bundle will be the set of vectors of length equal to 1. Yeah. Oh yeah, and then dm will just mean the fiber of dm over m, and sm will be the fiber of sm over m. And the proposition is that you can think of, or that there's an isomorphism from, so disk mod sphere. By this I'm gonna mean the bundle whose fiber over a point M is the disk bundle, is the tangent vectors of length 1 modulo the tangent vectors, length less than 1 modulo the boundary sphere of vectors length equal to 1. And I'm saying that this is, this is homeomorphic, or it's isomorphic to the fiberwise 1 point compactification of the tangent bundle. So here at every point you have an SN, and here at every point you have a disk mod a sphere. But this is homeomorphic to SN, and you can make this identification continuous, or very continuously over M. Okay. And so a while ago we talked about using the exponential map to show that there's this which one? Yeah, there's this map that I'm going to call P tilde. It's not a projection of so I'm calling P the projection map of the bundle, and P tilde is going to be this map from this disk bundle over M with a property that P tilde sends the fiber over M, or restricts to an embedding of the fiber over M into M, and that embedding sends 0 in the disk to M. Yeah, so I'm saying like there's a continuous way of identifying this this bundle of disks over your manifold, or like, I guess, a continuous way of taking the fibers of this disk bundle over M and embedding them into your manifold, and it uses this exponential map where you sort of flow along geodesics. And it's not canonical, but you can pick one. Okay, so let's define the scanning map. So what do we need to do? Given a configuration, which my advisor would always just write it like a squiggle and say, like, call it squiggle or a legible Greek letter or something. So I don't actually know the name of this Greek letter, but okay. Is this chi? I don't know. Okay, so we have
Psi.
Psi. Okay, we have some configuration, x run through xk in the configuration space, and we have some point M. And I guess our goal is to take this data, and we want a way of taking squiggle and M and producing an element in disk M mod sphere M, which is the same thing as the tangent fiber of M. So this is what we're trying to do, and the first step is we're just going to let squiggle M be the inverse image of P tilde applied to I guess this is that M is a typo. Yeah. So what you do is, what I'm saying is, okay, first, so P tilde restricts to give a map from disk M, gives an embedding of the disk into the manifold, and then you can think of squiggle as being a subset of the manifold. And what you do is you just intersect squiggle with the image of this embedding, and then pull back. So given the configuration, what you do is you look at the configuration in the disk, and then identify that small disk around M with the disk bundle in M. That's what squiggle sub m is. So in this picture, we have 5 points in squiggle and 2 points in squiggle sub m. Any questions? Okay. So yeah, so now we have, in this picture, we start with 5 points and then we get 2 points in a disk. And the issue is basically we want 1 point in the disk. We want 1 or 0 points in the disk. So what do you do? Well, let's reorder the points. So that in order of length, and we'll let D be 1/2 reordered by distance to the origin, and we'll let D be 1/2 the distance from the second closest point to the origin. And I guess we'll define this to be 1/2 if there isn't a second closest point. So if there's 1 or 0 points, there's no x2, and we'll just define this number to be 1/2. So yeah, so you do is you take the second closest point, and then the idea is if you look at half the distance from the origin to the second closest point, that number is going to be positive, and there's going to be at most 1 point in that ball. There might be 0, there might be 1. And then we'll let S sub squiggle sub m be x1 scaled by D, or the point at infinity, assuming that this is the point of the disk, and otherwise, if there's no x1, or if this point is outside the disk, you just let it be the point at infinity, so the equivalence class of the boundary sphere. Yeah, so basically what we're doing is we're saying you scale, you throw out this point, and you scale this point to be, possibly slightly farther away. Or another way of saying it is, what are we doing? We're just zooming in a little bit more, so now we only see at most 1 point. So I guess this thing is what I'm calling S squiggle sub m. And this is what we wanted. We wanted a way of what you can view as instead of viewing it as a configuration, you can just view it as an element of dm rel sm. This is an in, not an arrow. Okay. Any questions? Yeah, so so the scanning map is just going to be the map that sends a config. We need to send a configuration to a section. So given a configuration and a point, we need an element in the fiber, and we just use this construction. So you pick some disk, and then you look at what points are in that disk, and then you zoom in a little bit more, so you only see at most 1 point. So this seems a little bit ad hoc, and I'm going to later give a definition that is slightly less ad hoc. It still depends on arbitrary choices, but maybe it's slightly more natural. Okay. So to define the slightly more natural scanning map, I'm going to talk about relative configuration spaces. Yeah, so this will be analogous to what we did for free abelian groups. And if you remember, the definition of the scanning map in the case of free abelian groups involved relative configuration spaces. So this alternate description will also involve relative configuration spaces. So what's the definition? Well, let's just let conf m without a subscript mean the disjoint union of all the configuration spaces. Here, k is allowed to be, k runs from 0 to infinity. And if you have some subspace n contained in M, we're going to let the relative configuration space just be the quotient, where if any points are, if a point is an n, it vanishes. So this point is M1 through MK is equivalent to M2 through MK if M1 is an n. Yeah, and I guess this this isn't an equivalence relation, but take the equivalence relation generated by this relation. So in pictures, it's points. Here the blue is n, the black is m. Points in, you could think of it as points in m minus n, and they converge if they converge to points in n. Okay. So the first proposition is that if you look at the relative configuration space of points in a disk, rel sphere, it's going to be homotopy equivalent to Sn. So yeah, and this n will probably be easier to think. This Sn, it'll be easier to think of as disk mod sphere. So I guess my question. Any guesses at any natural maps between these two spaces? So one of the maps is going to be reasonably natural, and the other is going to be somewhat ad hoc. Zach, do you have a guess?
The one that goes from like right to left is like natural.
Is what?
The one that goes from dn mod Sn minus 1 to conf is natural because you just include.
Yeah. So what are we like? What's the image of the purple going to be?
Conf 1 of
Yeah,
dn mod.
it's going to be the
Sn
image of
1.
it's going to be the image of conf 1. Yeah. So this will be the configurations, or I guess and conf 0. So this will be configurations of at most. It is true that it's the image of conf 1. It's the So this is going to be the configuration space of most 0.
I mean the 1-point configurations.
Yeah, so it'll be 1 or 0 point configurations, because if you have 1 point in the disk, it could hit the boundary sphere, and then you'd have no points. So like what you can think of, so what we should do is we should think of this as like conf less than or equal to 1 dn Sn minus 1. I haven't defined this, but you should just think of this is going to be homeomorphic to the subspace where you have at most 1 point. And then the green map is going to be some like, zoom in and or scale and shove at most, or shove all but at most 1 point out to infinity map. Is that what you were saying, or you're saying something different? Also, like Nick, were you about to say something, or was it redundant with what Zach said?
It's redundant with what he said.
Okay, yeah. Okay, yeah. So what's the map? So you can, the disk is the same as configurations of 1 point in the disk, which you can map to configurations. Configurations of 1 point in the disk can include in configurations of all points into the disk, and then this has a quotient map to configurations in the disk relative boundary. And and then what you need to do is you need to just check that this descends to a map on the quotient. And so basically you need to check that the boundary of the disk all points in the boundary of the disk map to the same point, well, they're all going to map to the empty configuration. So it descends to a map like this. And so we'll check that this map is a homotopy equivalence by describing a homotopy inverse, which will be sort of similar to the map used in our first construction of the scanning map. Yeah. So what's the picture? Basically, we just want a way of saying shove all but one point out to infinity, but we want to do this in a continuous way. Yeah, so what we're going to do, we'll let f from this configuration space to R be half the distance between the origin and the second closest point. That's what we talked about before. So f of the configuration is going to be some number, is going to be always positive. So the reason why it's always going to be positive is because if you, what am I saying? If you have 2 points, if you have 2 points, they can't both be at the origin. So one of them is going to be off the origin. And I feel like this min with one thing I screwed up, but there's some construction that works. So then the key property is that when you intersect this with if you intersect the configuration with the ball around the origin of this length, you're going to have at most 1 point in the configuration. You might have no points. For example, like you might have 2 points that are equidistant from the origin. And then if you look at a ball, if your 2 points are the same distance from the origin, and then you look at the ball, it's going to contain neither of your 2 points. But it's also possible, that one of the points is way closer to the origin than the other one, and then it will contain that point. Okay, and then we'll let scale sub t be the map that just scales your configuration, and then we have a function. I guess the observation is that when you scale a configuration by this much, then it's in the image. So if you scale a configuration by 1 over f of the configuration, you're gonna have only at most 1 point. So what you do is here, when you're scaling, you're making the blue circle the gray circle, and this point your scales out of the disk. So I guess the convention is that you just get rid of that point, and then you're scaling this point a little bit. So I guess here maybe I should say we're interpreting if the length, if t times your configuration is outside of your disk, you just get rid of that point. So we're going to let f be the inclusion we talked about before, I guess we'll let x be the image. And so x is homeomorphic to a sphere, and so f is going to be the inclusion, and g is going to be the map that sends a configuration to this scaled version. And f and g are homotopy inverses. They don't exactly compose to the identity, but they compose to scaling, and then you can just unscale. So this is the idea of the proof. In pictures, what do? You just push all but at most 1 point out to infinity, and then the points vanish. You need to do this in a continuous way. Any questions? Okay. So now I'm going to define a new bundle. So this is, it has some fancy name, which maybe we'll justify this name. So I'm going to call it like classifying space to the power tangent bundle of configuration space, whatever that means. So concretely, what this is it's it's as a space, it's going to be the subspace of the manifold cross configurations in the disk bundle rel the sphere bundle, and then we're going to add the condition that the configuration lies entirely in the fiber over M. So what you should think of this as, like, what's the data? We have this point to M, and then we have a configuration of, so this point M, and we have a configuration in the disk around M, rel the boundary. And there's a projection map which just sends a point in the configuration to M, and this is a fiber bundle, and the fiber is just this relative configuration space. And then the next observation is that this fiber-wise one-point compactification of the tangent bundle is homotopy equivalent, like as bundles. You can do this in a way that respects the projection map to just the fiber-wise one-point compactification of M. So this both of these are homotopy equivalent to spheres. The fiber over M in both cases are homotopy equivalent to spheres. In this case, it's homeomorphic to a sphere. In this case, it's not homeomorphic to a sphere. But you can do this sort of pushing points out to infinity in families if you pick a Riemannian metric on your manifold. So you can get a way of identifying this bundle and that bundle. And this will in particular mean that the space of sections of this bundle and the space of sections of that bundle are the same. So we can construct a scanning map that instead goes to the space of sections of this bundle instead of that bundle. Okay, so now we get slightly easier definition in the scanning map, but it goes to a slightly weirder looking space. So you just to define the scanning map, I just need to tell you, given a configuration and then given a point in the manifold, I need to give an element to the fiber. Well, what do? You just take your disk and you intersect it with your configuration. And now if there's 2 points, you're not upset. So this isn't fully natural, but I think it's slightly more natural than the other construction. Any questions?
You see again where you send those, like say you get those 2 points, then what do you do with those?
Oh, then you're done, because like the scanning, this is an element of conf like dm sm. And that's what the fiber is. So like I've changed the codomain of the scanning map to be this thing. That space. So now it's going to sections of a different bundle.
Okay.
Yeah, so instead of saying, okay, I'm going to pick this bundle whose fibers are spheres, I'm picking a bundle whose fibers are these relative configuration spaces, but up to homotopy, they're spheres. Is the idea. So this is like a more complicated space, but then the scanning map is just like literally record what you see, and it doesn't matter how much you zoom in. You don't need to zoom in at all if you don't want to. It's just see 40 points. And then sort of the equivalence between this and TM dot, this, going from here to here involves zooming in more. So, in some sense, we haven't really done that much, but it's nice. I think it's nice to be able to think about it this way also. But this is somehow a more natural thing, and then you do this other step where you just say this bundle here, actually, we could replace this whole thing with just the fiber-wise one-point compactification of the tangent bundle. Yeah, because I mean, if you think about it, like in the case of free abelian groups, it was a bundle of Eilenberg McLean spaces, and our model for that was it was a bundle of relative configuration spaces. So here, you could also think about it as a bundle of relative configuration spaces. Any questions? Oh, sorry, one second. Sorry about that. I was just having dog issues. Okay. Yeah. So there's a theorem. I guess I'm missing the hypothesis that the manifold's non-compact, but the theorem is going to be that the scanning map induces an isomorphism in homology groups in the limit that k goes to infinity. I'll remind you what colimit means later. So here, what are the maps in this colimit? So recall we defined, for non-compact manifolds, we defined the stabilization map where you take a configuration and then you glue on a collar neighborhood of the boundary, and then you add a point in that configuration. Yeah, and then the manifold with a collar attached you can identify with the original manifold, since you can just apply some homeomorphism, and that has the effect of sort of pushes this point in, pushes all the points away from the boundary by a little bit. Okay, and we can pick a compatible stabilization map on the space of sections. So given a so M prime is M with this collar attached, and so given a section of given like a vector field over M and given a vector field over the collar, you can just glue them together to get a vector field over the manifold with a collar attached, and degrees add. So if you pick a degree k section over the manifold and a degree 1 section over the collar, you're going to get a degree k plus 1 section. The reason why you can glue things is because of this boundary condition. We require that they're going to be equal to infinity near the boundary, so that I'm drawing it like there's 0. Oh yeah, so I guess both. I'm drawing it like I forgot what the base points were when I made this picture. Sorry about that. Yeah, so in this green region, both of the sections are infinity, or in this picture, I guess I'm drawing it as if both the sections are 0 near on this green region, so you can glue them together. So then if you pick a point in this space, that gives you a map from here to here. And that, and then you can identify the manifold with the collar with your manifold again. And that, I guess at the end of the day, we get this map that increases the degree by 1. So you should think we're just sort of bringing in from the boundary a degree 1 section. And that's this composition is tau. Any questions? Sorry, I'm distracted by my dog. or any like requests for me to repeat any of this. Okay, so yeah. Oh yeah, so these maps, I guess we proved last, or no sense of time. Was it last class? What did we do last class? Oh no, it wasn't last class. A week ago, we proved that that these stabilization maps induce isomorphisms in homology in a range, increasing with the number of points. So the stabilization map for configuration spaces induces an isomorphism in a range in homology. These stabilization maps are just for the section space are going to be homotopy equivalences. And what's the proof is just you can construct a similar map where you stabilize by a degree -1 section. So you can let tau prime be the same construction, but now we put a degree -1 section near the boundary. And if you concatenate a degree 1 and a degree -1 section, you're going to get a degree 0 section. So tau and tau inverse are going to be homotopy inverses to each other. Yeah. Oh, maybe I should probably say more. Yeah, so like here we're stabilizing by adding a degree 1 section, which is like, you should think that we have a bunch of arrows pointing inward, and here we have a bunch of arrows pointing outward. And then if you, I guess this is a picture of tau prime. And then if you apply tau to this, that's going to have the effect of, now we stabilize by a degree minus, or degree 1, degree -1 section, then a degree 1 section. So here the arrows go outward, here the arrows go inward. And then what you need to know is basically you need to know that there's a path from this degree 1 section. I guess here it's this degree -1 section concatenated with a degree 1 section. You need a path in the space of sections to a degree 0 section. So you need to know that this section space is connected, but you can, that like the degree 0 component of the section space is connected. But you can take this to all be happening in Rn, and you can make your section sort of constant outside of disks, and then basically all you need to know is that loops 0, or to know that these are homotopy inverses, you need to know that the space of degree 0 sections is connected, and that follows from not a good explanation, but you can sort of think of, if I draw this blue disk around my two sections, that gives me an element. You can think of it as an element of maps from a sphere to a sphere, because the tangent bundle will be trivial over the blue disk. And then you need to know that the degree 0 component is connected, which follows from the fact that this is isomorphic to Z. Because this is the same thing as pi n Sn. Oh yeah, this is annoying. There was like a math overflow conversation or post, and someone said, like, what are proofs that like pi n Sn is Z? And then I said, like, oh, here's a proof using configuration spaces. And then someone's like, this is clearly circular. I'm sure you use that pi n Sn is Z somewhere in the proof. And until now, I didn't know where it was used. But, okay. Sorry, I'm happy to repeat some of this. I don't think this was that clear of an explanation. Okay, whatever. So the stabilization map for section spaces are homotopy equivalences. And if you pick your section here to be in the image of the scanning map, then you can make this diagram commute. I have no idea what that is. Yeah, so you can stabilize by bringing a point in from infinity, and then you can stabilize by bringing in a degree 1 section. And if your degree 1 section is sort of in the image of the scanning map for the collar, then you can make this diagram commute. And so, this statement about homotopy colimits having the same homology, here we're taking the colimit under the maps T, and here we're taking the colimit under the maps tau. That's saying in the limit they have the same homology. And then we'll use that to deduce the statement for finite k. Okay, so let me remind you what colimits are. So if you have a sequence of abelian groups, then we'll just define the colimit to be the direct sum of the abelian groups modulo the subgroup generated by A minus the map applied to A. So what this is saying is basically you take the direct sum of all these groups. So an element, an element in the colimit is just an element, a sum of elements in any of these groups at finite stage. But then you identify elements with their image under these maps. Yeah, so if all of these groups are subgroups of some big ambient group, and all of these maps are just inclusions, then the colimit is just the union. Yeah. On the other hand, like let's say this F map is 0, well then we're identifying everything in A0 with its image. So, or I guess everything in the kernel of these F maps doesn't contribute to the colimit because they're identified with their image, but their image would be 0. Okay, so here's an algebra question. Let's let Fk be the map from Z to Z. It's multiplication by K. So here, I guess all of the A's are just Z. What's the colimit of Z's?
Like identifying every integer with all of the integers that divide it?
Was this a question or a statement? I didn't quite.
The statement maybe?
Yeah, so it's so what you're saying is like, okay, we're identifying 1 with 1 over 1. Here we're, so maybe like what we should think is like, okay, if I have x here, I can sort of think of x as x over 2 here. And then I can think of it as x over 6 here. Certainly if x is divisible by 6 here, then it will be identified with that x. But, 5/6 is not an element here. And is this in the spirit of what you're saying, or is there, am I? Yeah. So this group has at least up to isomorphism, has a nice name. Any guesses at the name of this abelian group? It's not some like complicated like p-adic blah 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 thing that I don't know the definition of. Yeah.
Is it just Q? Is it just like rationals?
Yeah, it's just the rationals.
All right.
Yeah.
That's pretty cool.
Was also said in chat. Yeah. And then if you take, let's say you took all the maps just to be 2, you would get like the subgroup of the rationals given by fractions with like anything on the numerator, but only powers of 2 in the denominator. which is also like Z with 2 inverted. Yeah, so, probably some large portion of you, but maybe not all of you guys have seen localization. And so, colimits give you models of localization. Yeah, so here we're inverting multiplication by all the primes, so we're inverting everything. You get Q. I mean, it's not always a localization, but if you take it does give you a way of thinking about localization. Okay, so we're gonna, answer is Q. So we're gonna do like a homotopical version. So what we're gonna do is we're going to, so we have a bunch of spaces and maps. The homotopy colimit, so hocolim. Is going to be, we're going to, I'm missing a disjoint union. So it makes it like unreadable. Whatever. It's going to be the union over K. Where to write it? Union over K of your space cross an interval. So crossing when the interval doesn't change the homotopy type of the space. And then what we're going to do is we're going to glue these together. So we're going to identify one end of the interval, so like points of the form x, 1, with the other end of the interval for the next space. So with fk of x, 0. So what we're doing is, you take all of your spaces, cross them all with intervals, take their disjoint union, and then you glue one of the cylinders to the other cylinder along these attaching maps. Yeah, and then the let's stay on this picture. Yeah, so then the proposition is that the homotopy colimit, the homology of the homotopy colimit is just the colimit of the homology groups. And the point of like crossing with the interval is to make this true. If you didn't cross with the interval, you'd basically just get the union. So if your maps F were nice, it would still be true. Oh, and this interval is like part of is the is like the homotopy colimit. It's not the strict colimit. Yeah, so sometimes you don't have to cross with the intervals if your maps are sufficiently nice. Like if your maps are inclusions of a CW complex, then crossing with an interval doesn't matter. But for more pathological maps, this construction makes it true. Okay, so yeah, so in an example, if you take all of your spaces to be spheres and you take your map to be multiplication by degree k, sorry, to be a degree k self map of the sphere, then you get this what's called the homotopy colimit is a model of the rational is what's called the rational sphere. So it's a space whose what's its homology? Well, in degree 0, it's just Z, because we're taking colimit under the identity map. Like if you have a map between connected spaces, that map will induce the identity on H0. But these maps are degree K, so on Hn it'll induce multiplication by K. So the nth homology will be Q, the 0th homology will be Z, and all the other homology groups will be 0. So this is like an example of a more general construction that basically if and if you're like, oh, this is the rational sphere, I don't like this Z thing, you can take reduced homology, cross out that line. Yeah, so let's say if you've simply connected spaces, there's a functorial way of replacing your space with a space whose homology groups are equal to the homology group of your original space but tensored with Q. And similarly for any localization of Z. There's, weird things happen in degree 0 and 1. Is like H0 is a set, or sorry, pi 0 is a set, and pi 1 is like a non-abelian group. And so like this procedure will also localize homotopy groups, but it doesn't make sense to localize sets or non-abelian groups. So yeah, so there's some things you can do, but it's better behaved in the simply connected case. Okay, sorry, this was just like an aside. Yeah, so the theorem is that the theorem that we're going to prove next time, or sketch the proof of next time, is that the scanning map gives you a map from homotopy colimit for the configuration spaces under their stabilization maps to the homotopy colimit of the section spaces under their scanning map, and this is an isomorphism on homology in all degrees. And so then a corollary of that is we get, that the colimit of the homologies agree. And then, assuming we've proven that, we get a further corollary. So by homological stability, all of these maps in this homotopy colimit are eventually, or all the maps are isomorphisms once on homology, once you have at least 2i number of points. So, this I don't know why I wrote ho-colim on one side and colim on the other side. Yeah, so I guess what I'm saying is the homology of the homotopy colimit is just the homology. The ith homology is just the ith homology of configurations of j points once j is at least 2i by homological stability. And then here, because a typo, this should be I, this should be j. And then the homology of the homotopy colimit on the section space side is just the homology of any of the section spaces because all the maps are isomorphisms. So then, knowing that these two things are the same tells you that the, and knowing homological stability tells you that the ith homology of the configuration space of j points agrees with the section space once you have enough points. So this is the theorem we wanted to prove originally. And then the upshot is we just need to prove, because we know homological stability, we just need to prove that theorem. And that's what we'll do next time. Yeah, any questions?